Alright, example 4. List the potential rational zeros of this function. Okay, what we're going to be doing, we're going to be looking at this number and this number. Our p is going to be all of the all of the factors of negative 6. So in this case, positive negative 1, positive negative 2, positive negative 3, and positive negative 6. Q is going to be all factors of this number too. So positive negative 1, positive negative 2. So the potential rational zeros would be all possible quotients p over q. 1 divided by 1 is just 1. 2 divided by 1, that's just 2. 3 divided by 1 is 3. 6 divided by 1 is 6. 1 divided by 2 is 1/2. 2 divided by 2 is just 1, which we already have. 3 divided by 2 is 3 over 2. And 6 divided by 2 is 3, which we already have. So these are the potential rational zeros. If f has a rational zero, it will be found in this list, which contains 1, 2, 3, 4, 5, 6 times 2, 12 possibilities. Alright, I'll let you guys try the U-try. Okay, find the real zeros of this polynomial function and write it in factored form. So this is the same function as we had up here, so we already know the potential rational zeros. Now, f is a polynomial of degree 3, so there are at most 3 real zeros. Okay. There is one variation of the sign right in here, so there is one positive real zero. Okay. Now, if we plug in f of negative x, we get negative 2x cubed. This sign stays the same, but this sign changes. Okay. Now we have one variation of the sign here and another variation of the sign here. So there are either 2 or 0 negative real zeros. Okay, so we have our list of potential rational zeros. I will write it over here. Positive negative 1, positive negative 2, positive negative 3, positive negative 6, positive negative 1/2, positive negative 3 over 2. If you were to graph this on your graphing calculator, and I'm pretty confident you guys are all able to do that, so I'll just go ahead and do it here. The graph looks something like this, and try my best to draw this. Something kind of like that. Alright, so if you look at this, there are 3 zeros. 1 here, 1 here, 1 here. There's 1 positive real zero and 2 negative real zeros. Okay? If you look in the window, you will notice that this one is pretty close to negative 6. This one is somewhere between negative 1 and 0. And this one is very close to 1. Okay? So, from our list of potential rational zeros, we will test negative 6 to determine if it is 0. Let me change colors. So I'm going to plug in negative 6. So I've got 2 times negative 6 cubed plus 11 times negative 6 squared minus 7 times negative 6 minus 6. And if you do all that out, you end up with 0. So negative 6 is in fact a 0. Okay? Now, I'm going to use synthetic division here. Hopefully you guys remember this. We know that negative 6 is a factor. So I'm going to divide negative 6 into the rest of this. So I've got 2, 11, negative 7, negative 6. If you guys don't remember how to do this, ask me in class tomorrow, okay? I pull down the 2. 2 times negative 6 is negative 12. 11 plus negative 12 is negative 1. Negative 6 times negative 1 is positive 6. You add here, you get negative 1. Multiply, you get positive 6, 0. So if you factor this, sorry, f of x can be written like this. X plus 6, because we know that negative 6 is a factor. And from this here, we have 2x squared minus x minus 1. Okay? Now, any solution of this equation will be a 0 of f, because this, we call this equation a depressed equation. I'll write that down. Actually, let me use a different color. About green. This is a depressed equation because any solution, any 0 of f is a solution of this equation. Okay, so we can work with this equation to find the additional zeros of f. Hopefully you guys can see that this can be factored. This is x plus 6, and if I factor this here, I end up with 2x plus 1, x minus 1. So, these are our factors. X equals, oops, negative 6, negative 1/2, and positive 1. So here are my zeros, and here is the function in factored form. Alright. Alright, here I'm just going to list out the steps of what we just did, alright? Okay, so this is basically what we just did. First, we determine the maximum number of zeros, so basically just the degree of the function. Then we use Descartes' rule of signs to figure out how many, potentially how many positive real zeros and how many negative real zeros we can expect. Then we use the rational zeros theorem, that's the P and Q thing that we did, to list out any possible rational zeros that we might have. Then we graphed it, and we figured out what, probably what the zeros were going to be, and then we factored it to figure out the rest. Okay. Let's do another one. Alright, example 6. Let's try that again. Alright, example 6. Find the real zeros of this function here. Write f in factored form. Alright, we know that there are at most 5 real zeros. Okay? Descartes' rule of signs. If you look here, there's 1, 2, 3, 4 variations in sign. So there's either, I'm gonna write it this way, 4, 2, or 0 positive real zeros. Okay? And if you plug in negative f of x, or negative x into f of x, you end up with negative x to the 5th minus x to the 4th plus 4x cubed plus 8x squared plus 32x plus 48. There is only one variation in sign, so there is one negative real zero. Okay, if you graph this, the graph looks something like this. And of course, I mean for you guys to graph this on your calculators. Something like that. So you see that there are two zeros, one here and one here. Okay? This one, if you look at it at, sorry guys, this one, if you look at it on your calculator, you can kind of tell is negative 3. Okay, so I'm going to use synthetic division. Let me go back to purple. Negative 3 we're pretty sure is one of the zeros. So negative 3, negative 1, 4, 8, 32, 48. And then just go like this. So, sorry, I did the wrong one. Give me a sec. this one. I was actually doing this one. So we've got positive 1, negative 4, positive 8, negative 32, and 48. Pull down the 1, got negative 3, negative 4, positive 12, 8, negative 24, negative 16, 48, 16, negative 48, and 0. Okay, so now we see that this can factor as so. X plus 3, x to the 4th minus, minus 4 x cubed plus 8x squared minus 16x plus 16. Okay, now if you look on your calculator, you can also kind of tell that this one is positive 2. So I'm going to do synthetic division again. I'm going to divide 2 into my depressed equation. 1, negative 4, 8, negative 16, and positive 16. I'm using this equation now, not the original one. There's no reason to go to the original one. You know that if 2 is a factor of this equation, it also has to be a factor of this equation here. So 1, 2, negative 4, positive 4, 8, negative 16. Voila, 0. So now I'm going to factor this a little bit more. I've got f of x equals x plus 3, x minus 2, and now what I have here, x cubed minus 2x squared plus 4x minus 8. Sorry, I'm going into this side over here. Alright, now this can actually be factored by grouping. I've got x cubed minus 2x squared plus 4x minus 8. Sorry, guys. From this, you can pull out an x squared. So I've got x minus 2. And from this, I can pull out a 4. And I've got x minus 2. So this factors into x squared plus 4 and x minus 2. So my final factored form is x plus 3, x minus 2 squared, because there's 2 of them, x squared plus 4. Okay, now if you think about it, this makes sense because we knew there had to be 4, 2, or 0 positive real zeros. When we see only one positive real zero in the graph, that real zero is probably going to be squared. So there's 2 of them. Alright? So I'll also put this. Negative 3, 2, and this one isn't real. I'll let you guys do this one over here. Alright, solve this equation. The solutions of this equation are basically just the zeros. So we're going to do the same thing again. And, oh, you know what? I think this is just this equation from up here. Yep, it is. So, we pretty much already did it. X equals negative 3 and 2. Because the solutions of this equation are just the zeros, or when you factor it. Alright, let me write out these definitions. Alright, this theorem doesn't have a name, so I just call it a theorem. Every polynomial function with real coefficients can be uniquely factored into a product of linear factors and/or irreducible quadratic factors. Also, a polynomial function with real coefficients of odd degree, that's like 1, 3, 5, etc., has at least one real zero. Alright, bounds on zeros. Let f denote a polynomial function whose leading coefficient is 1. A bound m on the zeros of f is the smaller of the two numbers. Okay, so this will make a lot more sense when we do some examples, but the examples will be on the next video. Alright?